Your roof right now is 80 degrees Celsius, 60 degrees hotter than the air around it. Stanford put a fabric on that same roof, same sun, same heat, and it dropped to 5 degrees below the air. No electricity, no compressor, nothing. A $500 billion HVAC industry does not want you to know this exists. Let me say that again so it registers. A standard black roof under direct sunlight reaches 80 degrees Celsius. That is 176 Fahrenheit. Stanford measured this on their own rooftop in California. An aluminum roof, the kind people call reflective, still hit 40 degrees Celsius. That is 20 degrees above the surrounding air. Every roofing material you can buy at a hardware store absorbs sunlight, converts it into heat, and pumps that heat into your attic, your walls, your living space. Your air conditioner then fights that heat every hour, every day, every summer, and you pay for it. The average American household spends $719 between June and September on electricity. Gas, and air conditioning accounts for roughly 19% of all residential electricity consumed in this country. That is 2,365 kilowatt hours per household per year just to cool the air inside your home. Nationally, cooling accounts for 254 billion kilowatt hours of electricity annually in the United States alone. The Energy Information Administration confirmed that number. And globally, the International Energy Agency says cooling consumes nearly 20% of all electricity used in buildings. 20% of all building electricity on the entire planet goes to fighting heat that your own roof is generating. Now here's the part nobody told you, directly above your roof. Right now, as you watch this, is the coldest thing in the known universe. Outer space. The vacuum between the stars is roughly 3 Kelvin. That is minus 270 degrees Celsius. An infinite, permanent free heat sink that has existed since the beginning of the universe and will exist until its end. And between your roof and that cold, there is a gap, not a physical gap, a spectral gap. Between 8 and 13 micrometers on the electromagnetic spectrum, Earth's atmosphere is nearly transparent to thermal radiation. This is called the atmospheric infrared window. Any heat emitted at those specific wavelengths passes straight through the atmosphere, through the clouds, through the water vapor, through the carbon dioxide, and radiates directly into space. Every surface on Earth is already doing this to some degree. Your roof is radiating heat into space right now. But during the day, the sun pours so much energy onto that same roof that the outgoing radiation is completely overwhelmed. The roof absorbs far more than it emits. It heats up. Your house heats up. You turn on the AC. And a $525 billion HVAC industry collects its fee. In 2014, a team of engineers at Stanford University asked a simple question. What if we built a surface that reflects almost all incoming sunlight, so the roof never heats up, while simultaneously emitting as much thermal radiation as possible through the atmospheric window? What if we could turn a roof from a solar absorber into a space radiator? They published their answer in Nature, one of the most respected scientific journals on Earth. The paper is titled Passive Radiative Cooling Below Ambient Air Temperature Under Direct Sunlight. The lead authors are Aswath Raman, Mark Abu-Anoma, Lingxiao Zhu, Eden Raffaeli, and Shanhui Fan, well, all from Stanford's Department of Electrical Engineering and Department of Applied Physics. What they built was a photonic radiative cooler, 7 alternating layers of hafnium dioxide and silicon dioxide, each precisely tuned in thickness, deposited on top of 200 nanometers of silver, all on a silicon wafer substrate. The total thickness of the active layers is less than 2 micrometers, thinner than a human hair, thinner than a single red blood cell. This structure does 2 things simultaneously that no conventional material can do. First, it reflects 97% of all incoming sunlight. Not 90, not 95, 97. The remaining 3% is the only solar energy it absorbs. For comparison, a typical white roof reflects about 70 to 80%. Aluminum reflects roughly 90%, but still heats up to 20 degrees above ambient. The Stanford surface reflects so much sunlight that the solar heating term in its energy balance becomes nearly negligible. Second, the structure emits thermal radiation with extraordinary selectivity. It emits strongly and almost exclusively in the 8 to 13 micrometer atmospheric window, while reflecting radiation at all other infrared wavelengths. This means it dumps heat into space at the exact wavelengths where the atmosphere will not absorb it and send it back, while refusing to absorb the atmospheric thermal radiation that would otherwise heat it up. They placed this surface on a rooftop in Stanford, California. They tilted the apparatus 30 degrees toward the south to maximize solar irradiance during their winter testing period. A pyranometer measured the incoming solar radiation at over 850 watts per square meter. That is peak sunlight, the full force of the California sun bearing down on a surface smaller than a dinner plate. And the result was unambiguous. The photonic radiative cooler dropped to 4.9 degrees Celsius below the ambient air temperature. Not below the roof temperature, below the air itself, while the sun was shining. While 850 watts of solar energy were hitting every square meter around it. The black roof next to it was at 80 degrees. The aluminum was at 40. The Stanford surface was below the air. It had a net cooling power of 40.1 watts per square meter at ambient temperature. At 40 watts per square meter, using zero electricity, zero refrigerant, zero mechanical parts, and zero energy input of any kind. The researchers went further. They modeled what would happen if they could eliminate convective and conductive losses, if they could perfectly insulate the surface from the air touching it. Under those ideal conditions, the same surface would reach 19.5 degrees Celsius below ambient. That is more than 35 degrees Fahrenheit below the surrounding air temperature, from a surface sitting in direct sunlight, powered by nothing. Now you might think this sounds like a lab curiosity, a proof of concept. Interesting, but impractical. Except that it did not stay in the lab. In 2021, a team at Zhejiang University in China published a paper in Science, the other journal that sits alongside Nature at the top of global science publishing. They created what they called a metafabric, a hierarchical morphology composite textile that achieves passive daytime radiative cooling at industrial scale. In outdoor tests, the metafabric was 5 to 10 degrees Celsius cooler than cotton. When placed on a human body, it cooled the skin 4.8 degrees below what commercial cotton achieved under the same conditions. When draped over objects like cars, it reduced surface temperatures by up to 30 degrees Celsius. This was no longer a wafer on a rooftop. This was a wearable, rollable, manufacturable material that could be produced at scale. Separately, at Purdue University, mechanical engineering professor Julien Ruan and his team developed the whitest paint ever created. It reflects 98.1% of incoming sunlight, even more than the Stanford photonic surface, and cools outdoor surfaces by 4.5 degrees Celsius below ambient air temperature. The Guinness Book of World Records certified it as the world's whitest paint. The key ingredient is barium sulfate in varying particle sizes, which scatter different wavelengths of sunlight with maximum efficiency. The researchers estimated that painting the roof of a 1,500 square foot building with this paint could generate a cooling power equivalent to 10 kilowatts, comparable to a central air conditioning unit running at full power. Purdue is working toward commercial production at a target price of roughly $40 to $50 per gallon, the same as premium exterior paint. Then, in 2026, this year, a transparent radiative cooling film was tested on automobile windshields and demonstrated a cabin temperature reduction of 6.1 degrees Celsius, with a 20% reduction in cooling energy consumption. It allows more than 70% of visible light through, while selectively reflecting near-infrared radiation. The study was published in Energy and Environmental Science by the Royal Society of Chemistry. The film is transparent. You cannot see it, but it turns any glass surface into a radiative cooler. So let us take stock. Stanford proved the physics in 2014. Zhejiang turned it into fabric in 2021. Purdue turned it into paint in 2021. A commercial company called Sky Cool Systems, founded by the same Stanford researchers who wrote the Nature paper, is already manufacturing and installing radiative cooling panels on commercial rooftops. These panels connect to existing air conditioning and refrigeration systems and reduce their energy consumption by pre-cooling the fluid that circulates through them. The California Energy Commission funded a study on these panels. They work 24 hours a day. They require zero electricity, and they reduce the load on the AC compressor, which extends equipment life and cuts energy bills. A 2025 European study published in Energy in Buildings tested passive daytime radiative cooling materials on residential buildings across multiple climate zones. In Mediterranean climates, cooling energy savings reached up to 75%. 75%. 3/4 of the energy a household spends on cooling eliminated by changing the surface properties of the roof. A separate study tested radiative cooling coatings on concrete rooftops and measured a maximum surface temperature reduction of 21.1 degrees Celsius. On corrugated metal roofing, the kind found on agricultural buildings, warehouses, and millions of homes in developing countries, the average temperature dropped by 6 degrees. On clay tile, 6.4 degrees. This is not theoretical. These are measured reductions on real buildings under real sunlight. Now here's the math that the HVAC industry does not want you to do. There are currently around 2 billion air conditioning units operating worldwide. The International Energy Agency projects that by 2050, that number could reach 5.6 billion. 10 new air conditioners sold every second for the next 25 years. Global cooling demand is projected to more than triple. The HVAC market is $525 billion today and heading toward $1.2 trillion by 2035. Air conditioning alone is a $134 billion market. That growth depends on one assumption, that the only way to cool a building is to run a compressor that consumes electricity. The moment a passive material that costs $40 a gallon or a few dollars per square meter can reduce cooling loads by 75%, the economic foundation of that entire industry begins to crack. And there is a second calculation that almost nobody is making. Urban heat islands. Cities are on average 1 to 7 degrees Fahrenheit hotter than surrounding rural areas. In some cities, the difference exceeds 10 degrees. NASA has documented this extensively. The primary driver is that buildings, roads, and rooftops absorb sunlight and re-emit it as heat instead of reflecting it. Dark roofs are the single largest contributor. Now imagine an entire city where every roof is coated with a material that reflects 97 to 98% of sunlight and radiates the rest into space. You're not just cooling individual buildings, you're cooling the city itself. You're reducing ambient air temperature at the neighborhood level. You're shrinking the heat island. And every degree you reduce ambient temperature means every air conditioner in that city works less hard, uses less electricity, and costs less to run, compounding the savings across millions of buildings simultaneously. The technology behind this is not complicated to understand. It is sophisticated to engineer. Precisely tuning layer thicknesses at the nanometer scale, selecting materials with the right phonon-polariton resonances, optimizing emissivity profiles across the full infrared spectrum. But the principle is as old as the universe itself. Hot things radiate heat. If you point that radiation at the coldest heat sink available, outer space, and clear a path through the atmosphere for it to get there, you get cooling for free. The atmosphere has had this window between 8 and 13 micrometers since it first formed. The cold of space has been there for 13.8 billion years. The only thing that was missing was a surface smart enough to exploit both simultaneously while rejecting the sun. Stanford built that surface in 2014. Nature published it. The cooling power was measured at 40.1 watts per square meter. The surface went below ambient and direct sunlight. Then, Zhejiang scaled it into fabric that stays 10 degrees cooler than cotton. Then Purdue made it into paint that earned a world record. Then SkyCool commercialized it into panels that are already mounted on rooftops and saving energy right now. Then a European study showed 75% cooling energy savings in residential buildings. And yet, as of today, not one residential roofing company in the United States offers a radiative cooling product as a standard option. Not one home builder installs it. Not one building code requires it. The average American household still pays $719 every summer to run an air conditioner that fights the heat their own roof creates. 2 billion air conditioners are running on this planet right now. 5.6 billion are projected by 2050. The electricity they consume is accelerating climate change, which is increasing temperatures, which is increasing the demand for more air conditioners, a feedback loop that the IEA has warned could become one of the most critical energy challenges of the century. And the solution, or at least a massive part of it, is material that turns roofs into radiators, beams heat into the void of space, and cools buildings below air temperature without consuming a single watt of power. It exists. It is proven. It is published. It is commercialized. And it is being ignored because a $525 billion industry has no financial incentive to tell you about it. That is what this video is about, not just the science, not just how the atmospheric window works or what a photonic emitter does. This video is about the gap between what has been proven and what has been adopted, between what Stanford published in Nature and what your contractor offers you when you ask about a new roof, between what physics makes possible and what the market makes available. That gap is not an accident. It is an industry-wide blind spot maintained by the economics of selling compressors, refrigerants, and kilowatt hours to people who do not know there is an alternative. You now know. The question is what you do with it. A gallon of Purdue's ultra-white paint, when it reaches commercial production, will cost about the same as a gallon of premium exterior paint. A SkyCool panel is already available for commercial installation. A radiative cooling film can be applied to windows, car windshields, and glass surfaces. And the fundamental principle: reflect sunlight, emit through the atmospheric window, use space as your heat sink, can be approximated right now with commercially available high reflectivity white coatings that get you 80 to 90% of the way there for a fraction of the cost of running your AC for one summer. The physics does not care about the HVAC industry's business model. The atmospheric window is open, space is cold, and your roof is still 80 degrees because nobody told you it did not have to be. Now you know.